Tsunamis are awe-inspiring events. A wall of, well, water washing away whole cities in what, a couple of minutes? Wild! Plus, they can occur all over the globe. They happen wherever earthquakes happen underwater. Japan, the Philippines, Chile, Alaska, California. Except no, California earthquakes don't create tsunamis. Not from a lack of trying. The 1906 earthquake in San Francisco practically shook the city to pieces, but no tsunami. And again in 1989, during the Loma Prieta earthquake, they had fires, collapsed highways, brilliant news coverage. But tsunami? No. What's the deal, California? To answer this question, we need to understand how earthquakes, and by extent tsunamis, occur. Okay, time for some science. An earthquake is the sudden movement of Earth's crust, usually caused by energy being released at a fault. Faults are cracks in the Earth's crust. These faults are everywhere. They run down oceans, over land, and even through cities. Earthquakes can and do occur along any of these faults, but most are too small to be felt. However, not all faults are equal. Some faults are big, really big. Big faults make big earthquakes. Where are the biggest faults? Tectonic plate boundaries. Let's take a step back. For the uninitiated, here's Earth. Cut her in half and you can see the layers of the Earth. We're focusing on Earth's crust, here on the surface. The crust sorta seems like it should be one solid piece, but it's not. Instead, it's broken up into massive pieces called tectonic plates. The boundary, or fault, between these plates is where a lot of the action happens. Tectonic plates are moving. Even right now, they're scooting around at about the same rate your nails grow. That's only about 1.5 inches or so a year, way too slow to see or feel in our lifetime, but over thousands of years, these 1.5 inches add up. Take East Africa. Looking closer, you can observe that a lot of these lakes appear to be in a rough line, almost like they're all linked. In fact, these 4 lakes, Albert, Edward, Kivu, and Tanganyika, look like they might even share the same valley. That's because they do. These lakes were created by the same event, tectonic shifting. We can start to see what's going on when we draw in where the tectonic plates are. The Arabian Peninsula lies on, well, the Arabian Plate, here. Most of Africa sits on the creatively named Africa Plate, here. But not all of Africa sits on this plate. This section of Africa sits on a separate plate called the Somalian Plate, because, well, this is Somalia. Remember that all of these plates are moving. The African and Arabian plates are both moving northwest, but the Somalian plate is moving east. When 2 plates move away from each other, they take whatever land they have with them. Thus, East Africa on the Somalian plate is moving away from the rest of Africa. The result is called a rift valley, which forms as the plates move apart. Here comes a big rainstorm, and now these valleys are lakes, just like the lakes all over East Africa. This is particularly unusual in Ethiopia and Kenya. Unlike most other East African countries that use the lakes along the Rift Valley as their borders, these 2 nations have the rift zone running through their middles. This is either a good thing or a bad thing depending whether you're a glass half full or a glass half empty kind of guy. Rift valleys are the result of a divergent plate boundary. Divergent because the plates diverge or pull apart. Well, what about when 2 plates meet? That's a, wait for it, convergent plate boundary. Divergent boundaries make valleys, so it makes sense that the convergent boundaries make mountains. For example, this is the Indian plate, which is moving north, and this is the Eurasian plate, which is moving southwest. These 2 plates push against each other, pushing the land on top of them up. This is how the Himalayas are formed, or rather are forming. These plates are still moving, and so the Himalayas are still growing, a little over 1 centimeter a year. There's one more type of plate boundary called a transform boundary. This one is a little less obvious, but it is when 2 plates move past each other. The San Andreas Fault, that's a fault that runs through California, is a transform fault. Note that, that's going to be important later on. Wait, how are all of these plates moving? Convection currents. Let's go back to the mantle, the layer below Earth's crust. The mantle is a solid, but not like a solid. A little more like this. It's a solid as it holds its own shape, but it can also move under enough pressure and heat. It takes a lot of pressure and heat to move rock, but the mantle has that. More so towards the bottom, where the mantle is heated by the Earth's core, and where the pressure from all the rock above is greater. The mantle is heated down there, causing it to expand and rise up. The top of the mantle is cooler and under less pressure than the bottom of the mantle. So, as the mantle rises, it cools and sinks back down. This forms a current, a little bit like a treadmill, that pushes the plates along. You can liken this process to a lava lamp, which works using the same principle. Okay, that's cool and all, but what does this have to do with earthquakes? Excellent question. We know what happens when two plates push land together, but what happens when land is pushed against the ocean? In general, the crust with the ocean on it is pushed down, below the crust the land on top. This is oceanic crust. It's easy to remember because the ocean is on top of it. Oceanic crust is made of mainly basalt, as well as other rocks rich in iron and magnesium. This makes oceanic crust dense. On the other hand, continental crust, that's crust with land or continents on it, is made of less dense rocks composed of silica, like granite. Now, it's a bit counterintuitive to think of granite, or really any other rock for that matter, as less dense material. In our daily lives, a lot of what we interact with is a lot less dense than granite. This is why we use it as a building material. But when compared to oceanic crust like basalt, granite is a lot less massive than we realize. When these two plates collide, the continental plate is pushed up so the oceanic plate can slide below. This is called a subduction zone, as the oceanic plate subducts under the other. In theory, this is a smooth process. In reality, though, it's not. This is where earthquakes come from. We'll use Japan as an example. Northeast Japan lies in the Okhotsk Plate, which is a continental plate. Next to it is the Pacific Plate, an oceanic plate. The Pacific Plate is moving west towards Japan and is pushed down under the Okhotsk Plate. This is called a subduction zone. Note how as the Pacific Plate moves down, it catches on the Okhotsk Plate. Tectonic plates might move slowly, but they are extremely powerful. So powerful that the Pacific Plate pulls the Okhotsk Plate down with it. This bends and contorts the Okhotsk Plate. The farther the plate bends, the more potential energy is trapped in the plate, a little bit like bending a plastic ruler. Bending the ruler a little and it springs back a little. Bend it a lot and it springs back a lot. The Okhotsk Plate is held down by the friction it has against the Pacific Plate. Eventually, though, the pressure on the Okhotsk Plate will grow greater than the resistance from the friction. When this happens, the Okhotsk Plate springs back up, releasing all of that stored potential energy at once. Boom, earthquake. Okay, but what about tsunamis? How does shaking convert into a big wall of water? Remember, the Okhotsk Plate sprang up vertically. Now, imagine if the hypocenter of that earthquake, that is the point in the ground where the plate slips, is under the ocean. As the plate springs up, it pushes all of the water above it up too. All of this water spreads out as it's pushed up, creating waves that travel out from the epicenter in rings. This is what creates tsunamis. Generally speaking, tsunamis occur at convergent plate boundaries because the energy is being released up. Remember that California's fault, the San Andreas, is a transform fault. These two plates, the North American and the Pacific Plate, are not moving towards each other like a convergent boundary. Instead, they are moving past each other. When these plates get caught on each other and then released, all of that energy is being released sideways, not up. Energy released sideways can't push the water above it, and like that, no tsunami. Wasn't that fascinating? Of course, California still has extensive tsunami plans, but not because of the San Andreas, but because of earthquakes across the Pacific Ocean. After all, tsunamis are not our fault. Oh, I'm sorry. That joke was terrible. That was a terrible joke. I'm gonna crawl back into my trash can now. Goodbye.